Okay, ladies and gentlemen, this is the part 2 video for lesson 2.3, and we begin by talking about zeros of odd and even multiplicity. What I want to do first is have you guys write down what the definition of multiplicity is, and that is how many times a particular number is a zero for a given polynomial. So this is a little bit of algebra to review, and hopefully these next few examples jog your memory a little bit. So if I give you a polynomial written in factored form, let's just say x plus 2 times x minus 1, calculate the zeros here. So set the left hand side equal to 0, so I have 0 equals x plus 2 times x minus 1, and so each of those factors are now set equal to 0, so x plus 2 equals 0 and x minus 1 equals 0. So I have x equals negative 2 and x equals 1. Now, negative 2 and 1 are both zeros for this polynomial, and they occur only once. So my multiplicity is 1. Alright, let's change this and let's write another example as f of x equaling x plus 2 squared. Right, now let's calculate the zeros, set the left hand side equal to 0, so we have x plus 2 times x plus 2. Alright, and so set each factor equal to 0, so I have x plus 2 equals 0 and x plus 2 equals 0, so x equals negative 2 and x equaling negative 2. Now notice here that my 0 of negative 2 occurs twice, so that is a multiplicity of 2. And then finally, do one more example. So we have x plus 2, but let's this time cube it and multiply it by x minus 6. So 0 equals x plus 2 cubed times x minus 6. And by now, hopefully you have identified the pattern that my 0 is going to be x equaling negative 2, and it's going to have a multiplicity of 3. It will occur 3 times. And then I'll have a 0 of x equaling 6 with a multiplicity of 1. Alright, and so why is multiplicity important here in this section? Well, because depending on if the multiplicity is odd or even depends on how the graph will react at the 0, or at the x-intercept. So if r is a 0 of even multiplicity, then the graph touches the x-axis and turns around at r. If r is a 0 of odd multiplicity, then the graph crosses the x-axis at r. Regardless of whether a 0 is even or odd, the graphs tend to flatten out at zeros with multiplicity greater than 1. Alright, so let's look at our little chart here, and what I want you to do is copy down what I have here. Oops. So in very simple terms, if the multiplicity is even, we're going to have a bounce, and if the multiplicity is odd, we're going to have, what do I have, crosses. It's going to cross, instead of crosses, let's say crosses the x-axis. Alright, and looking at these graphs, you'll be able to see what we're talking about here. So in this first one down here, we have y equaling x minus 3 squared. Our multiplicity is even, so at my 0 of 3, notice I'm going to have a bounce here. Bounce means I'm going to get to the x-intercept, or I'm going to get to the 0, I'm going to hit it and then go back up. So the graph is tangent basically to the point x equaling 3. For this one here, I have a odd multiplicity. Alright, and so therefore, when I get to my 0, when I get to my x-intercept, I'm now going to cross the x-axis. Alright, and so you can look at these last 4 and kind of see that pattern occurring. Alright, example 3. We want to state the degree and list the zeros of the function. We want to then state the multiplicity of each zero and whether the graph crosses the x-axis at the corresponding x-intercept. Alright. So the first thing we want to do is we want to write down what the degree is. So the degree of this polynomial is 5. And if you expand that out in FOIL, you can get a degree 5 polynomial. The zeros are going to be x equaling -2 and x equaling 1. Now, state the multiplicity of each zero and whether the graph crosses the x-axis at the corresponding x-intercept. So remember, zeros, x-intercepts, solutions, roots, those things, they're all meaning the same thing. Alright, so let's say the multiplicity of x equaling -2 is 3. Therefore, the graph will cross the x-axis because the multiplicity is odd. Alright. Now I'm going to have to do some erasing here to make some room. Get rid of that last sentence. Alright. Now I'm going to say the multiplicity of x equaling 1 is 2. Therefore, the graph will bounce at x equaling 1 because the multiplicity is even. Okay, now we want to sketch this graph by hand, and there's a few things that we want to find first before we sketch. The first thing that we want to find is the end behavior. Alright, so my end behavior is going to be starting down and ending up. And I know that because I have a degree 5 polynomial, so my polynomial, the degree is odd, the leading coefficient is positive, and so that's how I know I'm going to get that end behavior that starts down and ends up. My zeros and the multiplicity So -2, my multiplicity is 3, and then my 0 of 1 has a multiplicity of 2. And then what I want to find is the y-intercept. So that's going to be f of 0 equaling 0 plus 2 is 2, 2 cubed is 8, and then 0 minus 1 is -1, squared is 1, so 8 times 1, it's going to give me 8, so 0, 8 is my y-intercept. Alright, and so what I'm going to do is I'm going to plot the y-intercept. Plot my zeros. Alright, and now use my end behavior, so I know I'm going to start down. So I'm going to start here in quadrant 3, and I want to end up in quadrant 4. Alright, so what I'm going to do is I'm going to start here, and I'm going to start down and go up to the x-intercept at x equaling -2. My multiplicity is 3, so it's odd, so I'm going to go through and I'm going to cross the x-axis. I'm going to go up to the y-intercept, come back down to x equals 1. My multiplicity there is 2, so it's even, so I'm going to have a bounce. I'm going to go back up where I came from. And this is a rough sketch of what the graph is going to look like. Alright, in example 4, we want to find all the real zeros of this polynomial. So what you want to do is take this and plug it in to your y equals. So you need your calculator, take that, plug it into your y equals. Change your x minimum to -10, change your x max to 10, your scale to 1, your y minimum to -50, your y max to 50, and your y scale to 1. When you hit graph, you are going to get something that looks like this. Well, not quite like that. Alright. It's going to look something like that. Alright, and so it's obvious that there's going to be one of our zeros here. So let's calculate that one first. So we're going to go to second calc. We're going to go all the way to 0. Alright, and then we're going to do our left bound, right bound, do that whole routine. Alright, we're going to guess, and we're going to get a 0 of approximately -3.10. Alright, now it appears, so I could probably even draw this a little bit more, it appears that this graph just intersects the right hand side of the y-axis at one spot. Alright, but remember we talked about hidden behavior, and it's important that we want to try and get a little bit of a closer look of what's going on with the graph here. It looks like it's intersecting the x-axis only at one point, but we want to double check and make sure. Alright, so what I want you to do is change your window to -0.5 as your x minimum, your x max to be 2.5, 0.5 your x scale, -1 your y minimum, 1 your y max, and your y scale to be 0.5, and hit graph. And okay, so what you'll see now, alright, is something like this. Alright, so it's a good thing that we checked for this hidden behavior, because now we see that we actually are going to have 3 solutions there. Alright, so go ahead and check those. just like you did, like we did our first zero. Hit pause, and then when you're finished, go ahead and hit play again, and we'll check our answer. Okay, so you should have calculated zeros at, again, we calculated this one earlier, but at x approximately being negative 3.10, x approximately being 0.5, x approximately being 1.13, and x approximately being 1.37. Alright, last problem is modeling, very similar to a problem we've done previously. Here though we have Dixie Packaging Company. They've contracted to make boxes with a volume of approximately 484 cubic inches. Squares are to be cut from the corners of a 20-inch by 25-inch piece of cardboard, and the flaps folded up to make an open box. What size squares should be cut from the cardboard? Alright, so we know that our volume equals 400. Our volume equals 484 cubic inches. And then our formula for volume equals length times width times height. And so I need to calculate the length, width, and height here. Well, I notice that these little squares right here have the dimensions x by x. Alright, so what's the length going to be? Well, the length here is going to be 20 minus 2x. That's this length here. And then this length right here, or this width, I should say, is going to be 25 minus 2x. So, and then my height is just going to be the x here. So my volume is going to equal x times 20 minus 2x times 25 minus 2x. Alright, and you know the length and the width are interchangeable here. So once we have that written down, go ahead and you're going to type that into your y equals, your y1. So type this whole thing in. And then what I want you to do in your y2, go ahead and type in 484. Alright, and why are we doing that? Well, we'll see that in a minute, but put this in your window, and then we'll see why we did what we did. So make your window like your x minimum negative 20, your x maximum 20, your x scale 1, your y minimum negative 1,000, your y maximum 1,000, and your y scale 100. Okay, so when you put that window, put those values into your window and hit graph, here's what you should see. And so now what we can do is find the intersection point of this line, y equals 484, and my graph. And so what that is going to tell me is I'm going to be able to calculate the x coordinates that give me a volume of 484. So what you're going to do now is go to second calc, and you're going to go down to number 5 to intersect, and then you're going to calculate the intersection points between the two different curves. Go ahead and do that, pause it, and then hit enter when you're finished. Okay, so here are the x coordinates that give you a y coordinate or a volume of 484. So x is approximately 1.22, x is approximately 6.87, and x is approximately 14.41. Now we have to consider the domain of our problem here. So if I look here at x, what that represents is the height of my box, and obviously x can't be negative. So my x is going to have to be greater than or equal to 0. Now, if I make x bigger than 10 here, right, what's happened? Then I get a negative answer in here. Alright, so my x has to be greater than or equal to 0 and less than or equal to 10. So I can cross off that answer there, and these are going to be my two answers. Alright, and so squares with lengths of approximately 1.22 inches or 6.8 inches should be cut from the cardboard to produce a box with a volume of 484 cubic inches. Alright, so I hope this helps, and hopefully you'll be ready to go for the homework problems tomorrow in class.